Now that you've learned what the building blocks of the atom are, electrons, protons, and neutrons, we're going to study how they're organized within the atom. Or actually, how the electrons are distributed in the different shells, or rather energy levels, that Niels Bohr identified. It is this distribution that's called electron configuration. But before we do that, we'll just take a small detour to visit this man, Dmitri Mendeleev. His big achievement was that he was the first one to organize the elements in a periodic table. In the middle of the 19th century, some 60 elements had been discovered. The relative masses had also been determined, so the chemists knew, for example, that the mass of a carbon atom was 12 times the mass of a hydrogen atom, while the mass of a lithium atom was only 7 times the mass of a hydrogen atom. So, what did Mendeleev do? When he arranged the elements by weight, he discovered that some properties repeated themselves with a specific periodicity. Such elements with similar properties he placed in the same group. The result was a periodic table that looked somewhat like this. One thing that turned out very well with Mendeleev's periodic table was that it happened to correspond to how the electrons are distributed in each element, that is, the electron configuration. Perhaps you can say that Mendeleev was a little bit lucky because neither the electron nor the electron shells had been discovered at this time. This is what a modern periodic table looks like. In the periods, the horizontal rows, the atoms have the same number of electron shells. In the groups, the vertical columns, the atoms have the same number of valence electrons. And what that means is exactly what I'm going to explain thoroughly in this video. First though, I'd like you to note that the atoms in a modern periodic table are arranged by atom number, not relative atomic mass, as Mendeleev first did. We have atom number 1 up here to the left, that's hydrogen, and atom number 118, the very last atom of the periodic table, down here to the right, organeson. We write about the order in the periodic table that the elements are arranged by atomic number. The electrons in the atom, they are then arranged in electron shells so that they get as low energy as possible. This means that they are placed as close to the nucleus as possible, because the closer they are to the nucleus, the lower the energy they have. Let's begin with the electron configuration for hydrogen and draw a model of a hydrogen atom here to the right. Hydrogen's atomic number is 1, which means it only has 1 proton in its nucleus. In my small model here, you can see that there's only 1 proton and no neutrons at all. The number of neutrons is 0. This means that the mass number for this nuclide is 1. Yes, there are 2 other hydrogen isotopes as well, with 1 and 2 neutrons, but I'm not going into them right now. Finally, we see that the atom has an electron in its K shell. Since the electron is negatively charged and the proton is positively charged, the total charge of the atom is 0. It is uncharged. The next element in the periodic table, it's helium, which I draw here. Helium has the atomic number 2, and you can also see that it has 2 red protons here in the nucleus. In the model of this helium isotope, there are also 2 neutrons. Therefore, the mass number for this helium isotope is 2 plus 2 equals 4. To balance out the 2 positive charges in the protons, there are also 2 electrons here in the K shell. Let's also draw the third element, lithium. Lithium has the atomic number 3, and that's because there are 3 protons in the nucleus. In this lithium isotope that I have drawn a model for, there are also 4 neutrons, so it gets the mass number 7. Now, there are also 3 electrons in this atom, but watch this. In the K shell, only 2 electrons can fit. The third electron cannot fit in the K shell, but must be placed in the next shell, the L shell. So, in the K shell, only 2 electrons can fit, but what does it look like for the other electron shells? We make a simple table like this, with shells number 1, 2, 3, 4, i.e. K, L, M, and N. And then we write that the maximum number of electrons is 2 in the K shell, 8 in the L shell, 18 in the M shell, and 32 in the N shell. There is a formula for calculating that too if you want, and that is, in shell N, then there is room for 2 times n squared electrons. But, and this is very important, in the outermost shell, whichever it may be, there is never room for more than 8 electrons. This is because having 8 electrons in the outermost shell is particularly stable, something that's called noble gas configuration. We'll look at the electron configurations for some atoms to explain that. So now it's time for another table, and this time of the bigger kind. And yes, you should copy it too, because it's a good one. In the table head, we enter element and atomic number, and then number of electrons in the K, L, M, and N shells. We start with hydrogen, which I happen to know has the atomic number 1, so let's enter this directly here. And since the atomic number is 1, it also has only 1 proton in its nucleus. We thus know that there is also only 1 electron, and we then insert it into the K shell. The L, M, and N shells are empty. The next element that we're going to study is helium. Helium has the atomic number 2, and thus has 2 protons in its nucleus, and then also 2 electrons to be distributed. They both end up in the K shell. Lithium, you may also remember for just recently that its atomic number is 3. Since there are then 3 protons in the nucleus, we should distribute 3 electrons on the different electron shells. We can put 2 of them in the K shell, but since the K shell is quite small, we can only fit 2 electrons in it. The 3rd electron must therefore be placed in the L shell. The next element in the periodic table is beryllium, which has the atomic number 4. Then beryllium also has 4 protons in its nucleus, and thus 4 electrons to be placed. 2 of them end up in the K shell, but then it's full, so the last 2 electrons end up in the L shell. The M and N shells are still completely empty. Now, we skip forward a little bit to fluorine, which has the atomic number 9. Fluorine then has 9 protons in its nucleus, and thus 9 electrons that we distribute like this. The first 2 electrons end up in the K shell, and the 7 that remain are placed in the L shell. After fluorine comes neon with the atomic number 10. There are then 10 protons in the nucleus, and thus 10 electrons to be distributed. First, 2 electrons in the K shell, and when it's full, we put the remaining 8 electrons in the L shell. Sodium has the atomic number 11. As usual, we know that there are 11 protons in the nucleus, and thus 11 electrons to be distributed. We first put 2 of them in the K shell. But how many should there be in the L shell? Well, it is only possible to fit 8 electrons in the L shell. That's why we put 8 electrons in the L shell like this. 8 plus 2 equals 10, so then we have 1 electron left, and it will then end up in the M shell. Now we jump forward a bit again, and we take a look at sulfur. Sulfur, I happen to know, has the atomic number 16. 16 protons then in the nucleus, and 16 electrons to be placed in the electron shells. First, we put 2 in the K shell as usual, and then 8 in the L shell. Now we're up to 10 electrons. 6 electrons are left to place, and they all end up in the M shell. If we jump forward yet another little bit, we arrive at argon with the atomic number 18. Then, of course, you know how many protons there are and how many electrons there are to be distributed. That's right, there are 18 protons and 18 electrons. 2 in the K shell, which is then full, 8 in the L shell, which is then also full. Now, we have placed 10 out of 18 electrons, and the 8 that remain we place in the M shell. If we take the next element in the periodic table, it will be potassium with the atomic number 19. As usual, 19 protons in the nucleus and then 19 electrons to distribute. 2 in the K shell and 8 in the L shell, and then both of those shells are full. We now have 9 electrons left to distribute, but how do we do that? In the K shell, the maximum number of electrons is 2. In the L shell, the maximum number of electrons is 8. And in the M shell, a maximum of 18 electrons can reside. Then you might think that the 9 electrons left, we can put them in the M shell. But then you forget that in the shell that happens to be the outermost, there can be a maximum of 8 electrons. Thus, the 19th electron cannot fit in the M shell, but must be placed in the N shell. Therefore, there are 8 electrons in the M shell of potassium and 1 electron in the N shell. Let's take a few more examples of this. Look here at zinc, which has the atomic number 30. As usual, it contains 30 protons and 30 electrons to be distributed on the different shells. 2 of them end up in the K shell and 8 in the L shell. Of the 30 electrons in the atom, we have placed 10 and thus have 20 left to distribute. How many could there be in the M shell? Well, there can be 18 electrons in the M shell, so we enter that in our table here. We then have 2 electrons left and they must live in the N shell. One last example now, and it is krypton, which has the atomic number 36. With 36 protons in the nucleus, there will be 36 electrons to place. 2 as usual in the K shell, then 8 in the L shell. We fill the M shell completely with 18 electrons as well, and then we can note that we have distributed 2 plus 8 plus 18 equals 28 electrons. We have 8 electrons left and they end up in the N shell. If you have now kept a close eye on this and copied the whole table, then we will encircle all these electrons as well. It is all the electrons that are in the outermost electron shell, and they are called valence electrons. They are important because they determine much of the properties of an element. And as you can see, since there can be a maximum of 8 electrons in the outermost shell, this means that the number of valence electrons is a maximum of 8. You can also see that some of the elements we listed in the table, they have the same number of valence electrons. Here we have, for example, hydrogen, lithium, sodium, and potassium, all of which have a single valence electron. Therefore, they also have properties that are similar to each other, which is why they are all in group 1 of the periodic table. Let's take an example now of a question that could be at the E level of a test. Enter the electron configuration for oxygen. We see here that the oxygen has the atomic number 8, and then we know immediately that the oxygen atom consists of 8 protons and 8 electrons. Yes, and also several neutrons, of course, but they're not interesting for the electron configuration. We can then set up a simple table like this, where we enter that there are 8 protons in the nucleus, and then we get 2 electrons in the K shell, and the 6 that remain in the L shell, like this. A few last words about valence electrons too, so you get that in your notes. The valence electrons, as I said, determine a lot of the properties of an element, and it was precisely these properties that Mendeleev noticed when he put together his periodic table. I also want you to learn that the further the valence electrons are from the nucleus, the easier they can be given off to other atoms. It is also true that the fewer they are, the easier they can be given off. And we write this as well, that 8 valence electrons are quite stable. The thing with 8 valence electrons, it is so important that we should dive a little deeper into it and talk about the rule of octets, or even better, noble gas configuration. It is like this, that all the noble gases, except helium, have 8 valence electrons. Having 8 valence electrons, or 2 for helium, is called noble gas configuration. Since the noble gas configuration is extra stable, it is often the case that atoms strive to achieve noble gas configuration in chemical reactions. They do this by giving off or taking up electrons in different ways. And this, how electrons are given off or taken up, is called that there is an oxidation or a reduction. That is something we will return to many times in these videos.